Alright, welcome to Lucky Lecture 13, Engineering 270. So, our topic today is indirect file registers. And this is sometimes a weird seeming topic, but it's actually incredibly useful. It's the thing that basically makes modern programming languages work. So, this is not so much about instructions, and it's definitely not about hardware. It's really about special function registers. And I want to look at the following special function registers. I want to look at FSR0 and FSRH, and also this register INDF0. And that's all we're going to talk about for the next few minutes. FSR0, high and low, it's a 16-bit register, actually 12 bits, and INDF0. And there's a mysterious footnote here on INDF0, footnote 2, which says, this is not a physical register. So what the heck does that mean? We've got metaphysical registers now inside our PIC processor. So what is INDF0? Well, its address is FEF, okay, in hex, so 0x FEF. So suppose I say something like increment file register INDF0, right, which we know we get translated into an operand of EF with an access bit set to 0 so that we put an F in the front. But we would just write increment file register INDF0. If this was pretty much any other register in the processor, what would we expect to have happen? It would read the contents of this register, add 1 to it, write it back in, right? But that's not what happens with this register because INDF0 is not a physical register. So what does happen when we say increment INDF0? The following very strange thing. We have FSR0, H and L, so collectively it's a, think of it as a 16-bit register. We have these two things and they refer to a location in our data memory. So think of this as a 12-bit number, right? And our data memory has, addresses that are 12 bits. If we look at this 12-bit number in here, that's the address of some file register. This instruction will increment that file register. Okay, let's think about this. It does not increment INDF0. That's not even a physical register. It does not increment FSR0. It does not increment FSR0H or FSR0L. What it increments is the file register with the address given by FSR0H and L. So this is an indirect reference. And it's something that you've encountered before in programming languages, but may not have thought about how this gets implemented in hardware. So let's look at an example. Suppose FSR0, and I'm going to, for simplicity, I'm just going to talk about the register FSR0, kind of like we talk about timer 0. But we understand FSR0 is actually this composite of FSR0, H, and L. So I may be putting things in here that take more than 8 bits, but think of this as a 16-bit register essentially, comprised of these two 8-bit file registers. So suppose FSR0 is equal to hex 20. And suppose file register 20 contains the number 12. If I say increment file INDF0, what happens? The processor looks at FSR0, it sees a 20, it takes this instruction as saying increment file register 20. And so this 12 gets changed to a 13. And if I repeat this instruction, FSR0 is 20, this says increment file register 20, this now changes to a 14. But now suppose I change through some other instructions FSR0 to be X30. And let's suppose file register 30 contains a 0 right now. I execute the exact same instruction, increment file register INDF0, but now the processor says, oh, FSR0 is 30. He wants to increment file register 30. and it changes this 0 to a 1. So a single instruction, increment file register INDF0, can end up incrementing different things in your file register memory. In the previous case, it incremented file register 20, but now it's incrementing file register 30. Because the actual operand is not coded in this instruction, the actual operand is in this file register called FSR0, pair of file registers. So it's an indirect way of addressing an operand. We specify INDF0, we code it as FEF, but the processor sees that and says, oh no, I'm not going to increment file register FEF. I'm going to look at FSR0, whatever value is in there, I'm going to take that as the operand. Oh, it's a 30, she wants to increment file register 30, I'll go ahead and add 1 to that. Okay, so indirect addressing. It's an essential concept in computer science to be able to do this, and different processors have different ways of doing it. This is the way that this PIC processor does this. And once you understand how INDF0 and FSR0 work, we can deal with all these other things. We can deal with post-DEC1 and pre-INC2 and all these. They're all just variations on the theme. But let's take a look at another example of how we might actually use this, and I'm going to get into a mix of pseudocode and assembly language here so we don't get bogged down on assembly language details. But let's write a little snippet of code. And I'm going to put a comment here which says clear file registers from hex 20 to hex 40. Now we could do this with 32 instructions. We could say clear F0x20, clear F0x21, clear F0x22. We could just write all these instructions explicitly. But let's do this with a loop. Okay, so here's what this would look like in pseudocode. So copy hex 20 into FSR0. And then I'm going to say clear file register INDF0, and then I'm going to say increment file register FSR0, and I'm going to say go back up here, and I'm going to say do this 32 times, or maybe 33 times, because there's actually 33 numbers between here. Don't worry about the iteration count. But here's the essential detail, right? I'm going to clear INDF0, I'm going to increment file select register 0. So FSR0 is initialized to 20. The first time this clear is executed, it clears file register 20. Now I increment FSR0, so now FSR0 is equal to 21. And when I say clear INDF0, it clears file register 21. And then we increment this to 22. And when we say clear, it clears file register 22. And we keep doing this up to and including the point where FSR0 equals hex 40. And when we clear INDF0, it clears file register 40. And presumably we exit our loop at that point and we go on to do something else. So 2 instructions basically with a bit of looping logic allows us to march through our file registers and clear all of these locations. And we can start doing all kinds of things with this that we could not do otherwise, or would at least be very cumbersome to do otherwise. For example, add contents of file register 17 through file register 25 hex. Okay, well, how do we do this? Copy 17 into FSR0, clear out wreg, and then we're going to do a loop. And our loop will say the following. It'll say add wregister to file register INDF0 and put the result back in W. So just think about the first time we execute this. FSR0 is 17. INDF0 means file register 17. So this instruction effectively says add the W register to the contents of file register 17 and store the result in W. And since W started at 0, W is now the contents of file register 17. And now we say increment file select register 0. So FSR 0, which was 17, is now 18. And let's say if FSR 0 is not 26, go to loop. So we come back to loop, and now, since FSR 0 is 18, this instruction says add the W register to file register 18 and store the result in W. So it reads file register 18, adds that to W, which already had the contents of file register 17, stores the result in W. So W is now the sum of file registers 17 and 18. And we're going to increment FSR 0 to 19. And when we come back here, it's going to add the contents of file register 19 to W. And as we go through this loop, W is the running sum of file registers 17, 18, 19, and so on, all the way up through and including where we add file register 25, after which we increment FSR 0 to 26. And since it's equal to 26 now, we won't iterate back to loop, and we'll continue on with other stuff. So we're basically treating memory like an array, and we're using this FSR as an index into memory, right? With an array, when you say x bracket I, we're saying we don't want to use the value of I, we want to use I as a pointer, there's that word, into memory, right? A pointer at the ith element of this array x. That's all that's going on here. Okay, so next lecture we're going to dig into some of the mechanics of using this structure, but make sure you understand this basic concept of indirect access and file register selection, and then we'll start building on those mechanics.